All right, so on Friday we said there are a few different definitions used for acids and bases. We said Arrhenius described acids as molecules that produce protons in solution, where bases produce hydroxide anions, and then we saw examples of those. And then we saw later on that Bronsted and Lowry said, well, not all bases produce hydroxide anions. Some of them don't even have oxygen in their molecular formula, so they can't. So they came up with a new definition saying that acids donate protons and bases accept protons, and that the proton is handed off between the acid and the base in that transfer. All right, so today what we're going to do is start off talking about strong versus weak acids and bases. So what makes a strong or weak, oh my goodness, acid or base? All right, the big thing to remember is that strong acids or bases dissociate completely. Into ions. And let's take an example of that. A classic strong acid would be something like HCl. And if you put in hydrochloric acid, which is a gas, into water, the hydrochloric acid is going to completely dissociate, meaning it's going to completely break apart, and it's going to give up its proton to water. So water at that point will have an extra hydrogen and a positive charge, so it'll be H3O plus, and it will be Cl minus. So what this means is that because HCl is strong, we're going to have 100% ions in solution. So because of this, we often show strong acids and bases using a one-way reaction arrow, meaning it's an irreversible reaction. When it forms ions, those ions won't combine and then reform the starting materials. All right? Weak acids and bases are a little bit different. Do not dissociate completely. Meaning that some stays as starting material. All right, so I'll show you an example of a weak acid, although it's not one that's safe. This is hydrogen cyanide. Really, really toxic stuff, but it's one of the weak acids off of our chart. And hydrogen cyanide, if you put it into water, can also act as an acid. Therefore, it could give water a proton, meaning that water has gained an extra hydrogen and a positive charge. And then what charge will the cyanide have, the Cn? Have to be negative to cancel everything out, right? So in this reaction, we typically don't show it with a one-way reaction arrow because we know a lot of this remains as unreacted starting material. So what chemists like to do is they show this with equilibrium arrows. And I really like to show it this way. So it's almost like a two-way street where it says a little bit of it's actually getting pushed to the right-hand side, but most of it's staying on that left-hand side. So most of it's staying as starting materials. Showing that starting materials, and I'm going to abbreviate that, are favored. That doesn't mean that you don't have any ions in solution. It just means you don't have completely dissociated ions. You might get maybe 1 or 2% of this in solution. So very low concentration of ions. Does that make sense? It's a little bit confusing, but equilibria reactions are really important in chemistry. If you ever see these double-headed arrows, that means you have a mixture of starting materials and products in solution, not just products when the reaction is over. Okay. I did want to make an important note, though. This is something that students mess up a lot, is that an acid's strength does not equal concentration. Some students think if you have more and more of an acid, shouldn't that make it a stronger acid? Not necessarily. An acid's strength is an intrinsic property. Meaning it's something you can't change. You can't change it by making something more concentrated. It's defined by the molecule itself. So it is a little bit confusing that way. Does that make sense? All right. So we already discussed one other area, but I wanted to go back and revisit it, and this is called neutralization. And neutralization is a pretty simple concept. It's when you combine an acid with a base. And what pH do you typically achieve when you neutralize something? Does anybody remember from lab? 7. So you combine an acid with a base in the appropriate ratio to reach a pH of 7. All right? The products, whenever you neutralize something, are no longer acids and bases, right? Because it's right smack in the middle. Instead, what you get is water and a salt, right? And the salt, like I said before, could be any ionic compound. So it could be sodium chloride, it could be magnesium chloride, it could be anything that's a cation and anion pair, right? All right, so let's take a look at some of these. Let's say I've got sodium hydroxide and hydrochloric acid. If we mix these two together, we know that sodium hydroxide's a base, HCl is an acid. What we're going to do is take the hydroxide from the base and the proton from the acid, and we're going to make water out of it. And then if we think about what's left over, we've got sodium, which is normally Na+, and we've got chloride, which is normally Cl-. So to me, it looks like the charges are all bouncing out. So I'm just going to write our leftover material as NaCl. So what we're getting is water and a salt out of this acid-base reaction, right? So it's a common thing for Arrhenius acids and bases. All right, let's try another one that's a bit harder. Let's do CaOH2. What would this compound be called? Not covalent, so we don't need mono, di, tri, tetra. We don't need those prefixes. Be calcium hydroxide, exactly. So this is going to be a base. And let's mix it with HCl again. It's a nice simple acid. This will be our acid. Just like before, we know that we're always going to get water out of this. All right, so if we look at this, it's going to get a bit more complicated. So what I'm going to do is actually break this down into pieces. And I'm going to say, all right, if we look at calcium hydroxide, we've got Ca, which is normally 2 positive. It's in group 2A. And then we've got 2 hydroxide anions. That's why we put them in parentheses and the 2 on the outside. And then over here, we're going to react it with HCl, which is a covalent compound. And if I look at this, I could say, all right, one of the protons from HCl could react with one of the hydroxide anions to create one water molecule. Is this neutralized, though? I don't think so. We still have more hydroxide left over. In the end products for a neutralization reaction, we don't want hydroxide. We want water and a salt. All right? So the quick solution to this is to say, well, let's just add in more HCl. Because like I said, we have to have these mixed in the appropriate ratio. So if I do this, what I'm going to do is add in a coefficient here. Say 2 HCl's will be combined together with 1 equivalent of calcium hydroxide. And when we mix this together, it looks to me like we're making 2 molecules of water, or 2 equivalents of water. So I'll put that over here. And now we need to think about what's left over and whether or not that makes sense. So if we do this reaction down below, the calcium is still hanging out. And then it looks like we have 2 chlorines left over. If we rip off the proton from a chlorine, it must have a negative charge, right? So to me, it looks like each of those 2 chlorines has a negative, which should cancel out the calcium, which has a 2 positive, which means our final salt that we're making for this reaction would be CaCl2. So this is going to be the salt left over. The key thing to remember is when a reaction is neutralized, you don't want any hydroxide anions floating around because that's a base, and you don't want any protons floating around because those are an acid, right? So your leftover salt should just be something like a cation and an anion, but that anion shouldn't be hydroxide. Does that make sense? All right. So now what I want to do is talk about some kind of odd examples, especially ones related to environmental chemistry. And this is the reaction of water with non-metal oxides first, and then we'll do metal oxides. All right, so a non-metal oxide means we're dealing with some sort of element on the right-hand side of the periodic table, not a transition metal, not anything in group 1 or 2, right? So a good example of this that you probably heard a lot about in the news is carbon dioxide, right? So carbon dioxide is produced whenever we burn fossil fuels. So natural gas, oil, gasoline, you name it. When you burn it, you get CO2. If you combine this CO2 with water, you get H2CO3. This is carbonic acid. All right, let's take another non-metal oxide and see what is produced. All right, sulfur dioxide. Sulfur dioxide is produced primarily from burning coal. So if you burn coal, there's often sulfur trapped inside of that coal. And when you burn it, it will oxidize and form sulfur dioxide. When sulfur dioxide mixes with water, essentially what will happen is over time this will get converted into H2SO4, which is sulfuric acid. So there seems to be a trend here, right? Whenever we take a non-metal oxide and react it with water, we're producing in the end some sort of compound that is an acid. So it reacts with water to form acids. This is a really big issue, right? If you think about CO2, most of the time when people talk about it, they're referring to climate change, meaning the warming of our planet. However, CO2 also acidifies all of our waterways, including our oceans, which is a huge problem. Yeah?
Where does extra oxygen come from?
Yeah, I'm not showing the full net reaction, so let me change this to a dashed arrow. This is a lot more complicated than I'm making it appear. The main takeaway I want you to know from this is that non-metal oxides plus water equals some sort of acid. We're not going to get into the whole environmental chemistry aspect. The reality is the equilibrium for these is really complicated. So when CO2 mixes with our waterways, let's say a lake, a pond, a stream, our ocean, will the pH go up or down? It'll go down, right? It's another reason why seltzer water or carbonated water, if you drink it, tastes kind of bitter or sour. It's slightly more acidic than your normal fresh water. This is causing a lot of problem in our local ecosystems. If we have time, I'll show you a video later. Sulfur dioxide was a big problem, especially in the 1980s when we were burning a lot of coal. If we have sulfur dioxide going into our atmosphere, mixing with water, it's going to produce sulfuric acid in our clouds. And when those clouds rain, we have what's referred to as acid rain. Who's heard of acid rain before? Yeah, big issue. So if you actually look in like places like West Virginia, downwind of a lot of the coal-powered plants, you'll see these big swaths of forest that have been killed due to the acid rain being produced from those plants. What they've done as a way of counteracting that is they put these big scrubbers on top of the plants, and basically that means the smokestack is designed to absorb most of that sulfur dioxide. It can't absorb all of it, but they're getting pretty good at trapping like over 90% of it that's being emitted. So they're trying to figure out ways to make this a little less hazardous. All right, if we have time, we'll come back and watch this ocean acidification thing. We may wait until later on in the term though. All right, let's switch gears and talk about reactions with metal oxides now. And water. So the previous ones we were looking at were all nonmetals. What do you think likely will be formed if you react a metal oxide? Probably get a base, right? So it will form a base. So an example of this would be something like calcium oxide plus water. If you mix these together, you're going to get calcium hydroxide, and we know because it has hydroxide in it, it must be a base. Same thing with potassium oxide. If you mix this plus water, you're going to get 2 equivalents of potassium hydroxide. Each of these, though, like I said, is creating a product that now has hydroxide in it, and therefore is going to be a pretty good base. Typically, these aren't much of a concern for environmental chemistry. It's the non-metal oxides that cause a lot of the problems. Does that make sense? All right, last but not least, we've got to talk about pH. And I know you talked about pH in lab a little bit, but we'll come back and hit it again. I really like showing this because it was a sign I saw in a natural food store. Kind of cracked me up. They had a pH chart. The first thing that stands out to me is the scale. What's wrong with the scale? It should be 0 to 14, not 0 to 10. So they're off on the scale. And then if you look closer at it, they have pH 10. They're listing lemons and limes. Do you think lemons and limes have a pH of 10? No, what's their pH probably closer to? Probably closer to like 1 or 2, right? Lemons and limes are acidic. They shouldn't have a high pH. They should have a low pH. So some of these make me laugh. As you go down there, there's even worse ones than those. Let's see. I'm trying to remember the worst one on here. Where is it? Oh yeah, microwave foods have a pH of 3. Lack of sleep has a pH of 3 apparently. So oftentimes when you see these new products being advertised, a lot of them are just goofy. The big one that's all over now is they have high pH water that they claim will make your body more alkaline and therefore more healthy, that's a complete load. I would ignore anything that talks about pH of water. Just drink normal water. You'll be fine. You don't need the weird alkaline water. It won't do a dang thing. All right, anyways, moving on. If we look at a correct pH scale, the main thing to remember is that the scale goes from a pH of 0 to a pH of 14. So the scale should be a pH of 0 to 14. And like I said, this is acidic, the closer you get to 0. And then we go all the way over to basic on the other side. So the closer we get to 14, the more basic things will become. If you think about a lot of the stuff in your house, a lot of it you can actually predict just based on taste. So hydrochloric acid is basically the same thing as gastric juice, right? It's just a slightly different makeup of all the different chemical compounds. So when you throw up, you get that weird, gross taste in your mouth. That's an acid. Soft drinks are also acidic. Lemon juice is also acidic. Vinegar, very acidic. Urine is actually acidic. A lot of people don't know that. Rainwater is acidic. Why is rainwater acidic? Anybody know? Based on our last topic? Yeah, it's saturated with carbon dioxide. So it's absorbing the CO2 in our atmosphere. So rainwater is surprisingly acidic. Saliva is a little bit acidic, but usually closer to the neutral range. Milk is a little bit acidic due to some of the acids, the fatty acids found in milk. Pure water, meaning it hasn't been exposed to CO2, should be neutral. And then we get into the more basic things like blood is surprisingly acidic, surprisingly basic. Egg white, bile, that's what comes out of your gallbladder, milk of magnesia, baking soda, and sodium hydroxide. All right, so now the question is, how do we calculate pH? I'm not sure if Adrian went over this in lab. Did he? No? Okay. So pH is actually a mathematical measurement. And pH is the negative log of the concentration of protons in solution. All right? So another way of remembering this is P is a mathematical term that equals negative log. So it's just a fancy new term that we're looking at. All right? We can also do this with POH, where we find the negative log of the concentration of hydroxide in solution. And if we look at the concentration units for both of these, how do chemists measure concentration? Molarity, right? So it's measured in moles over liter, which is molarity. So we can calculate pH and POH of various solutions if we know the concentration of protons or hydroxide anions in there. All right, let's do the inverse of this though. Let's say we know the pH, but we don't know the concentration. Then we've got to do some log rules. So we could say that the concentration of protons in solution is going to be equal to 10 to the negative pH. Conversely, if we look at the concentration of hydroxide anions in solution, it's going to be equal to 10 to the negative POH. So we've got 4 different equations that we can now use. We can find pH here, we can find POH here, we can find concentration of protons, and we can find concentration of hydroxide anions in solution. The cool thing with this is we can actually directly relate pH to POH as well. So we've got 1/5 one. And this one's actually pretty easy to remember. pH plus POH equals 14 So we've got 5 different equations, and we can actually use this one to interconvert between the equations on the left-hand side with the equations on the right-hand side. All right, so let's try one. And your pod deals with similar problems to this. Oh, practice. So what is the concentration of protons in lemon juice? And if we go back to our chart, lemon juice has a pH of 2.1. All right, so we've got a couple different equations that we need to consider, right? So let's write out all those equations. We said pH is negative log of the concentration of protons. We said that pOH can be negative log of the concentration of hydroxide anions. We said that concentration of our protons is going to be equal to 10 to the negative pH. And then we said concentration of hydroxide anions is going to be equal to 10 to the negative pOH. All right, which of these equations do you think we're going to need to use? The first, second, third, or fourth? So right now it says calculate the concentration of H+. To me, looks like this one's the only one where we have concentration of H+ isolated. So let's take this one out and say, all right, concentration of H+ is going to be equal to 10 to the negative pH, which we said the pH was 2.1, so it's going to be 10 to the negative 2.1. And if we find the concentration using our calculator, it should come out to 0.0079. And the units are going to be in molarity or moles per liter. So this would be our final answer. Does that make sense? So the key thing that typically trips people up is remembering which equation to use. It's a little bit tricky. All right. Let's skip this one and come back to it, and then I'll give you another example one first. All right, so what is the pH of a 1 molar solution of HCl? So make sure that you pick the correct equation and then plug this one in. All right, show of thumbs, who thinks they got it? I see like one thumb, 2 thumbs. All right, let's maybe do this as a class. The key thing is starting out with the correct equation. So we need the equation where we're isolating pH. So if we think about the only one that was offered, we said that pH is going to be negative log of the concentration of H+. All right, in this case, the concentration of HCl is going to be the same as the concentration as H+, because it's a strong acid. So in this case, this will equal the concentration of HCl, because HCl completely dissociates into H+ and Cl-. All right, so now let's work this. We've got pH is going to be negative log of 1.0, which means pH is going to be what? 0. So you can have a pH of 0. It's kind of one of the weird aspects of working with logs. Does that make sense? So double check that you type it into your calculator correctly with the negative log of 1. Negative log of 1 is just 0. Yeah, so it might be a calculator issue. All right, I'll show you my favorite slash sad example of this in action. All right, so I mentioned ocean acidification. One of the troubling aspects of ocean acidification is when our oceans become more acidic, it actually will start eating away the shells of a lot of small sea animals because their shells are made of carbonates, which are bases, right? So over time, those shells essentially disintegrate, those little embryos die, and then there's nothing to eat for the larger animals that rely on them as a food source. All right, so prior to the Industrial Revolution, the pH of the ocean was measured to be about 8.25 globally. Today, the global pH of our oceans is about 8.14, which seems like a pretty trivial change in pH. And it's projected to go to a pH of 7.80 by the year 2100, so the end of the century. How much more acid is present today in our oceans? So I gave you a good formula to work on. So it says the current concentration divided by the pre-industrial concentration minus 1 times 100 will give you the percent increase. So let's try to do this together. The current concentration of acid, we said that the concentration would be 10 to the negative pH. Okay, so let's plug that in. And today the pH is 8.14, so it'd be 10 to the negative 8.14. It's projected, that's today's concentration. Pre-industrial concentration, we said, was, 8.25, so it'd be 10 to the negative 8.25 on the bottom. We can subtract 1 by this. We can multiply it by 100, and that should give us our percent increase from the pre-industrial levels to today. So let's try this on your calculator and see what answer you get for the percent increase. Find an answer. Does anybody want to share their answer? 28.8. All right, so compared to pre-industrial levels, our ocean water today has 28.8% more acid in it. Or I should say increase in the proton concentration, because that's what we were calculating. That's a pretty shocking increase, right? You think about what would happen if all of a sudden you started eating 28.8% more food every day, or started consuming 28.8% of anything in a given day more than what you used to. It'd probably throw your body all out of whack, right? So it's unhealthy for our planet. All right, let's do the next one though. What is the projected increase from pre-industrial levels to the year 2100? So basically in a 100-year span. So our projected pH is supposed to be 7.80, so we'll do 10 to the negative 7.80. That's our projected concentration. And we'll divide that by the pre-industrial level concentration, which was 10 to the negative 8.25 minus 1 times 100. Let's figure out what the projected increase is from pre-industrial levels to the end of this century. Who thinks they got an answer for this one? Anybody want to share their answer? What do you think? Yeah, so about 182% increase, right? I went to a talk a few years ago from a NOAA scientist, and he said in no uncertain terms, in the next 50 years, all of the coral reefs on our planet will start to die, regardless of where they are on the planet. Our planet is, in many ways, in dire shape right now, and it's unfortunate, in my opinion, that we focus all this energy on global warming, when the other side of that same coin is ocean acidification, and arguably that's going to be the first impacts that we're going to see as a community that lives on the ocean and on Puget Sound. All right, one last thing before you leave. For the pod, I wrote down a few hints for you in the notebook. The first one is just asking you to calculate the molarity. Second one is to use the concentration from part 1A to solve for POH, and then convert from POH to pH. And then for part 2, it says the molarity of your acid, meaning your proton, is going to be the same as the molarity of your HCl. And then the last part says find pH first, and then convert pH to POH. So I've got some hints on here if you do want to check OneNote while you're doing your work. All right, I'll see you all on Thursday.